Hello students, welcome to grade 12 chemistry revision lesson on chemical equilibrium. In our today's lesson, we will learn about reversible and irreversible reactions, characteristics of chemical equilibrium, application of equilibrium constants and reaction quotients. At the end of this section, you should be able to differentiate reversible and irreversible reactions, describe characteristics of chemical equilibrium, define equilibrium constants, show the relationship between Kp and Kc, define reaction quotients. Reversible and irreversible reactions. Reversible reaction. Now this is a chemical reaction that results in an equilibrium mixture of reactants and products. In reversible reaction, at equilibrium, both reactants and products are present. Two-directional reaction. In reversible reaction, reactants react and form products. In the same way, product converted into reactant. Therefore, reversible reaction is a two-way reaction from reactant into product, from product into reactant. Do not go to completion. Reactants react and form products. We use two half-headed arrow markers. You see, we use this arrow for reversible reaction. What about irreversible reaction? This is a chemical reaction which proceeds only in one direction. Irreversible reaction proceeds from reactants into product. It is a one-way reaction. Go to completion. Reactants are completely converted into product in irreversible reaction. Reactants react and form products. We use a single arrow to show the reaction is irreversible reaction. Attainment and characteristics of chemical equilibrium. Chemical equilibrium is a state in which the rates of the forward reaction equal the rates of the reverse reaction. Students, a reaction is said to be equilibrium reaction if and only if forward rates are forward equal are reverse rates. Concentration of the reactants and products remain constant. In equilibrium reaction, there is no apparent change in concentration of reactants and products. Concentration of reactants and products is constant, no change. Equilibrium is dynamic process. In equilibrium reaction, the process is dynamic, not static. That means reactants react, form a product. At the same rate, products are converted into reactant. Is dynamic process, not static process. For example, the reaction dinitrogen tetraoxide is converted into nitrogen dioxide. Now this is equilibrium reaction. You see, this is concentration time graph. Reactant, its concentration decrease. You see, concentration of product nitrogen dioxide increase. After some time, equilibrium is established. At equilibrium, there is no change in concentration of reactants and products. You see, concentration of the reactants decrease, concentration of the products increase. At equilibrium, no change in concentration of the reactants and products. Now this is concentration versus time graph for this equilibrium reaction. This is rate versus time graph for this equilibrium reaction. You see, forward rates depend on concentration of the reactant. You see, forward rates decrease. Reverse rate depend on concentration of the product. Forward rates increase. At equilibrium, forward rates are forward equal reverse rates. Equilibrium achieved, rates are equal. Characteristics of chemical equilibrium. What are the characteristics of reaction at equilibrium? The reaction is reversible in nature. Yes, it is a two-way reaction. One, the reaction takes place in a closed container, in a closed vessel. That means during the reaction, reactants and products are neither added nor removed from the reaction vessel. Therefore, the first characteristics of chemical equilibrium is that the reaction must be take place in a closed vessel, in a closed container. Two, the rate of the forward reaction equal the rate of the reverse reaction. For chemical equilibrium, for a reaction at equilibrium, forward rates are forward equal reverse rates. Three, all the reactants and products are present at equilibrium. For a reaction at equilibrium, both reactants and products must be present. The microscopic properties like temperature, pressure, volume, and concentration do not change with time. If these properties changed, now the equilibrium reaction is disturbed. Therefore, the properties like temperature, pressure, volume, and concentrations must be kept constant. The equilibrium is dynamic in nature. Reactants react to form a product at the same time, at the same way. Products converted into reactant is not static, it's dynamic. The concentrations of reactants and products are generally not equal. As we said, in chemical equilibrium, for reaction at equilibrium, concentration is constant. No apparent change in concentration of reactants and products. The free energy change of the reaction is zero at equilibrium. For equilibrium reaction, the Gibbs free energy change delta G equal 0. If the Gibbs free energy change for a reaction is less than 0, then the reaction is spontaneous reaction, proceed by itself. If the Gibbs free energy change delta G is greater than 0, the reaction is non-spontaneous reaction. But if delta G equals 0, the reaction is at equilibrium reaction. Equilibrium expression and equilibrium constant. Consider the generalized reaction AA plus BB to form CC plus DD. Now this reaction is equilibrium reaction because for equilibrium reaction we use a double arrow. You see, double arrow. Now a reaction is said to be at equilibrium reaction if and only forward rates are forward equal reverse rates are reverse. Now the forward rates depend on concentration of reactants. Therefore, forward rate equal K forward times concentration of M to the power A times concentration of B to the power of B equal reverse rate depend on concentration of the product. K reverse times concentration of C to the power of C times concentration of D to the power of D. We can write this as K forward divided by K reverse equal concentration of C to the power of C times concentration of D raised to D divided by concentration of M to the power of A times concentration of B raised to B. But concentration of C raised to C times concentration of D to the power of D divided by concentration of A to the power of A times concentration of B raised to B is equilibrium constant Kc equal Kc. Therefore, Kc equal K forward divided by K reverse. For a reaction involving gaseous reactants and products, we have this relation Kp equal partial pressure of C to the power of C times partial pressure of D to the power of D divided by partial pressure of M to the power of A times partial pressure of B to the power of B. This is for reaction in which reactants and products are in gaseous states. Note, the concentration of solids and liquids never appear in the equilibrium constant expression because concentration of solids and liquids is constant. Therefore, in Kc expression, equilibrium concentration terms which involve solids and liquids do not appear. For example, write the equilibrium constant expression for the following reactions. Calcium carbonate is in equilibrium with calcium oxide and carbon dioxide. Write the equilibrium constant expression for this reaction. Now Kc for this reaction, Kc equal concentration of carbon dioxide, CO2, concentration of carbon dioxide raised to its coefficient, which is 1. Note that concentration terms which involve solid and liquid do not appear in the equilibrium constant expression. Therefore, Kc for this reaction is concentration of carbon dioxide. What is the equilibrium constant expression for this reaction? Kc for this reaction, Kc equal concentration of hydrogen carbonates, HCO3 minus times concentration of H plus raised to its coefficient, which is 1, divided by concentration of carbon dioxide, CO2. This is liquid. Liquids, concentration terms which involve liquid do not appear in the equilibrium constant expression. Therefore, the equilibrium constant expression for this reaction is Kc equal HCO3 minus concentration times H plus concentration divided by carbon dioxide concentration. Relation between Kc and Kp. This is the relation between Kp and Kc. Kp equal Kc times R is universal gas constant having value 0.082 atmosphere liter per mole Kelvin times temperature. This is temperature in Kelvin to the power of delta N. Delta N is change in number of mole. Delta N equal the summation of number of mole of product minus the summation of number of mole of reactant. For example, for the equilibrium reaction, the value of the equilibrium constant Kc is this at 1069 Kelvin. Calculate the Kp for the reaction at this temperature. You are asked to calculate Kp for this reaction because reactants and products are in gaseous state. Now Kp equal Kc times RT change in number of mole equal the value of Kc is 3.75 times 10 raised to minus 6 times R is universal gas constant having value 0.082 atmosphere liter per mole Kelvin, mole times Kelvin times temperature T. Temperature T in Kelvin is 1069 Kelvin, 1069 Kelvin to the power of delta N. Change in number of mole is the summation of number of mole of product minus the summation of number of mole of reactant. Summation of number of mole of product is 2 plus 1 stream delta N. Delta N equal 2 plus 1 stream minus the summation of number of mole of reactant is 2. See? 3 minus 2 is 1. Therefore, this is 1 delta N. Now Kp equal 3.75 times 10 raised to minus 6 times this times 1069 is 3.3 times 10 raised to minus 4. This is equilibrium constants in terms of Kp. Application of equilibrium constants. What does the value of K? What are the applications of equilibrium constants? Kc. 1. The value of Kc predicts the extent of reaction at equilibrium. The extent at which reactants are converted into product is predicted by looking at the value of Kc. 2. Tells about the relative concentration of reactants and products or equilibrium position. One position of equilibrium, Kc can have 3 types of values. Case 1, when Kc equal 1, Kc is greater than 1, Kc greater than 1. What does this mean? As we said, Kc equal Kc for the reaction, for reaction of type A plus Bb to form Cc plus Dd. Kc is concentration of C raised to C times concentration of D raised to D divided by concentration of A to the power of A times concentration of B raised to B. Therefore, Kc is the ratio of concentration of product to that of the reactant raised to their respective coefficients. Now, Kc is greater than 1 means formation of product is favored. You see? Kc greater than 1, product is favored at equilibrium. Case 2, when Kc is less than 1, when Kc is less than 1, formation of product is not favored. What is favored? Formation of reactant is favored. When Kc equal 1, the reactions favors neither products nor reactants. Therefore, the value of Kc tells us the relative concentration of reactants and products. When Kc is greater than 1, formation of product is favored. When Kc is less than 1, formation of reactant is favored. When Kc equal 1, neither reactant nor product is favored. 2. Extent of reaction. Extent to which reactants are converted into products. If Kc is greater than 10 to the power of 3, if Kc is a very large value, now products predominates over reactants. You see? Or you can say the reaction proceeds nearly to completion. If the value of Kc is very large, the reaction proceeds nearly to completion. Look at this example. The reaction of hydrogen. The reaction of hydrogen H2 gas with oxygen O2 gas to form water. 2H2O liquid. Now Kc for this reaction equal 2.4 times 10 to the power of 47. You see? The value of Kc is very large. This showed that this reaction proceeds nearly to completion, goes to completion. Therefore, the value of Kc tells us how reactants are converted into products, extent to which reactants are converted into products. B, H2 gas plus Cl2 gas to form 2HCl gas. The value of Kc is this, 4 times 10 to the power of 31. Again, the value of Kc is very large. The reaction goes to completion. C, hydrogen gas plus Br2 gas to form hydrogen bromide. Again, the value of Kc is very large, 5.4 times 10 to the power of 8. Now this reaction proceeds nearly to completion. Therefore, if the value of Kc is very large, greater than 10 to the power of 3, then the reaction goes to completion. 2. If Kc is less than 10 raised to minus 3, or if Kc is very small, then the reaction proceeds hardly to completion, rarely to completion. You can take this as an example, the decomposition of water into hydrogen and oxygen. Look at the value of Kc. You see, Kc 4.1 times 10 raised to minus 48 is very small. This shows that this reaction proceeds hardly to completion, rarely to completion. Again, nitrogen gas plus O2 gas to form nitrogen monoxide. The value of Kc is very small. 3. If Kc is in the range of 10 raised to minus 3 and 10 the power of 3, what does this show? There is appreciable concentration of both reactants and products are there in the equilibrium mixture. Look at this for the reaction of hydrogen with I2. You see this reaction, H2 gas plus I2 gas to form hydrogen iodide 2Hi gas. Now this is equilibrium reaction. The value of Kc equal is 57. This number, this value is found between 10 raised to minus 3 and 10 the power of 3, 1000. This showed that there is appreciable concentration of both reactants and products, which is hydrogen iodide. B. Also gas phase decomposition of dinitrogen tetraoxide to nitrogen dioxide. You see, the value of Kc is 4.64 times 10 raised to minus 3. Now this value is found between 10 raised to minus 3 and 10 the power of 3. There is appreciable concentration of dinitrogen tetraoxide and nitrogen dioxide in the equilibrium mixture. Therefore, the value of Kc will tell us relative concentration of reactants and products. Again, it shows extent to which reactants are converted into products. Application of reaction quotients. Note that for the reaction AA plus B to form CC plus DD. Now this reaction is equilibrium reaction. The reaction quotient, which is denoted by the symbol QC, reaction quotient equal concentration of C to the power of C times concentration of D to the power of D divided by concentration of A to the power of A times concentration of B raised to B. Now, the reaction quotient, which is QC, predict the direction of the reaction at any stage, at any time. It shows direction of the reaction and describe or decide whether the reaction has attained equilibrium or not. 1. When QC is less than Kc, when the value of QC is less than the value of Kc, equilibrium constant, the reaction will proceed in the forward direction. Formation of product is favored when QC is less than Kc. More product will be formed till the equilibrium is reached. 2. When QC is greater than Kc, then the reaction proceeds from product into the reactant. Formation of reactant is favored. More reactants are produced before equilibrium is attained, before equilibrium is reached. 3. When QC equal Kc, then the reaction is at equilibrium. When the value of QC equal Kc, the reaction attained equilibrium. Therefore, the reaction quotient or QC predict direction of the reaction at any stage, at any time. For example, for the reaction B to 2N, now this reaction is equilibrium reaction. Its equilibrium constant is 2. Suppose 3 moles of A and 3 moles of B are introduced into 2-liter flask. In which direction will the reaction proceed to attain equilibrium? Students, as we said, the reaction quotient, which is QC, predict direction of the reaction. Therefore, you have to calculate the value of QEC to know direction of the reaction. Now, the value of QEC for this reaction, QEC equal concentration of A to the power of 2, concentration of M to the power of 2 divided by concentration of B, concentration of B. Concentration by definition is number of mole divided by volume. Therefore, concentration of M is 3 mole divided by its volume is 2. 3 divided by 2 to the power 2 divided by concentration of B. Again, number of mole divided by volume, which is 2 liter. 3 divided by 2. Now this is 3 over 2 equal 3 over 2, which is 1.5. Now compare QEC with KC. You see, the value of KC is this. QEC is less than KC because QEC is 1.5 less than KC is 2. Now the reaction proceeds from reactants into products before equilibrium is attained, before equilibrium is reached. In which direction will the reaction proceed to attain equilibrium? In the forward direction. In the forward direction, or from left to right. Will the concentration of B increase, decrease, or remain the same? You see, the reaction proceeds from B to 2M. Therefore, the concentration of B decreased. Concentration of B is decreased. Decreased. 2. What is the QEC value for this equation? Which direction will direction shift given this? The value of KC is 1. To know the direction of the reaction, your first step is to calculate the value of QEC. Now QEC for this reaction equal concentration of carbon dioxide coefficient, which is 1, times concentration of hydrogen divided by concentration of carbon monoxide times concentration of water H2O, equal concentration of carbon dioxide is 2 times concentration of hydrogen is 2 divided by concentration of carbon monoxide, which is 1, times concentration of water is 1, which is 4. Now compare QEC with KC. You see, the value of QEC is 4. QEC is greater than KC because QEC is 4 greater than 1, which shows the reaction proceeds from right to left. Here it says what is the QEC value. The value of QEC is 4. Which direction will the reaction shift? The reaction move from products into the reactants, or from right to left, right to left. Therefore, concentration of the product decrease before equilibrium is attained, and concentration of reactants increased. Calculating the equilibrium concentrations. How can we calculate equilibrium concentrations of both reactants and products? For example, look at this example. 3 mole of PCl5 kept in 1 liter closed reaction vessel was allowed to attain equilibrium at 380 Kelvin. Calculate compositions of the mixture at equilibrium. Now, the reaction is at equilibrium. PCl5 is a gas in equilibrium with PCl3 gas plus Cl2 gas. Initial concentration of PCl5 is concentration by definition is number of mole divided by volume. 3 divided by 1 is 1 molar. 3 molar. 3 initial concentration. Initially we have no PCl3 and Cl2. 0. Change minus X. Let X amounts of PCl5 be dissociated. Concentration of PCl3 is increased by X plus X. This is plus X. Equilibrium concentration of PCl5 is 3 minus X Equilibrium concentration is x. Then set equilibrium constant for this reaction. Kc for this reaction, equilibrium constant, Kc equal concentration of PCl3 at equilibrium is x times concentration of Cl2 at equilibrium is also x divided by concentration of PCl5 at equilibrium is 3 minus x equal equilibrium constant for this reaction is 1.80. Now x times x is x squared divided by 3 minus x equal 1.80. Now this is the same as x squared equal 1.80 into 3 minus x. Now this equation is quadratic equation because x squared plus 1.80x minus 1.80 times 3 equal 0 is a quadratic equation. We solve for x using the quadratic formula, which is minus b plus or minus b squared minus 4ac divided by 2m. Using this formula, the value of x is 1.59. The value of x equal 1.59. Now, equilibrium concentration of PCl5 is 3 minus x. You see, PCl5, 3 minus the value of x is 1.59, which is 1.41 molar. Equilibrium concentration of PCl3 and Cl2 is the same, which is x. The value of x is 1.59. Students, in our today's lesson, we learned reversible and irreversible reaction. Reversible reaction is a reaction which can proceed in both directions, is a two-directional reaction from reactant into product and from product into reactant. But irreversible reaction is a one-way reaction. Reactants are converted into product. For irreversible reaction, we use a single arrow. For reversible reaction, we use a double arrow. We also discussed characteristics of chemical equilibrium. As we said, a reaction is said to be equilibrium reaction if and only if forward rates equal reverse rates. This is one of the characteristics of equilibrium reaction. The other characteristics is the reaction must take place in a closed vessel, in a closed container. Concentration of reactants and products remain constant at equilibrium. These are some characteristics of equilibrium reactions or reactions at equilibrium. We also discussed applications of equilibrium constants and application of reaction quotient. As we said, equilibrium constants show us relative concentration of both reactants and products or equilibrium position. Equilibrium constants predict direction of the reaction, extent to which reactants are converted into product. This brings us to the end of our today's lesson. Until next time, goodbye.